And I'd like to welcome Irina to give the next talk in our series of steering committee presentations. And she's going to talk about atmospheric river impacts in Antarctica, from precipitation to melt. Okay, Irina.
Thank you, Tom, and thanks everyone who could make it today. And I hope that I can get some questions afterwards from also after the recordings. I'm just looking forward to your feedback to this ongoing work. So this work is about the atmospheric river impacts in Antarctica, and I will cover different impacts that they have, so both in precipitation and in melt. So just a little bit about myself. I'm working at in Portugal right now at the Center for Environmental and Marine Studies in University of Aveiro. And this work is actually, it's a collaboration with a lot of colleagues around the world, like in different countries. So just to start with the background, with the motivation, so why we care about the melt and precipitation, and so in both ice sheets. So here is the satellite measurements from 2003 to 2019, showing the mass loss from Greenland and Antarctic ice sheets. And we see that in Greenland, we have the majority of the coastal basins, and then we see on the map, and then below this is the mass changes at the grounding line. So we see that there is mostly the loss of mass, and this we know now. So the surface melt is becoming the major the major driver of this mass loss. And we have also large variability in snowfall, but the surface melt is now becoming more important than the increase in the snowfall. And in Antarctica, we see that the picture is quite different. So we see also primarily mass loss. So this is again from satellites over the West Antarctic ice sheets, and this also big parts of the Antarctic Peninsula. While over the East Antarctica, we majority we have gain of mass, and then only some areas that we have the loss of mass. So primarily in the Wilkes Land, and then in the Amery ice shelf, and then also the ice shelves on the Queen Mount Land. But here is also we see on the coast on the Queen Mount Land, there is really important gain of mass, and also we see this this contrast between the eastern and western parts of WISE in the gain of mass in the in this eastern part of WISE, and mostly the loss of mass in the western part of WISE. And that was also highlighted in the previous talk about this, the contrast. So we see that the Antarctic ice sheet is really, so it's really heterogeneous. And if you look at the mass changes in the grounding line at the bottom, so we see again that in the West Antarctica, so the most basins, they again they show loss, but the Queen Mount Land, specifically in East Antarctica, there is gain. So what is happening in terms of the snowfall and the melt, both surface and basal melt, it's understanding. So it's ongoing work right now. So, and here the recent work from Renaud et al. In 2019. So they published. It was a contribution to the INBI estimates, and here so I'm just showing this work from Renaud, because it's really showing by the basin. So we have the Antarctic Peninsula and the WISE and East Antarctica. So the changes in the different components of the total mass changes, and we see again. So the blue line, this is the surface mass balance. And we have, while we have important loss of mass, so the ice discharge, so we have, this is the majority in Antarctica, so it's really the ice discharge that is driving the loss of mass, while the precipitation, so the surface mass balance, we see that it's in all regions of Antarctica, so Peninsula, West and East, and so the total Antarctica, we see that it's actually really strong, large interrannular variability, and we have also in the East Antarctica, we have more gain of mass, and then there is more loss. So it's really changing and influencing a lot of the interrannular variability and also the future projections. So in the surface mass balance, we have an important impact of extreme precipitation events, and that was a paper by Turner et al. In 2019. So here on the map shows the percentage of the extreme precipitation events, which is the 90th percentile of daily precipitation. So we see that more than 40% over Antarctica, and then at some parts of the coastal areas, even more than 60% of the total annual precipitation is explained by extreme precipitation events. So that's another important point when we talk about atmospheric rivers. And another work I would like to highlight regarding precipitation in Antarctica is that we have not only snowfall, but we have also rainfall over the coast. And that's recent work published in Sauvignon et al. In 2000, so just this year. So here in the coastal stations, so we see here on the left, these are the observations. So we see that we have different counts of days. So this is the histogram showing how many days per year we have with rainfall. And here in the Antarctic Peninsula, we have really a lot of rainfall days over the years. And then even in the West Antarctica and East Antarctica, the coastal stations, we see that there is some amount of days with rainfall. So this is the dark blue is rainfall, and then we also count the drizzle. So this is based on the SYNOP observations. And while the coupled models, which are used for projections for the future, are not really well in reproducing rainfall in the present climate, but still they are all agreeing that in the future there will be increase in the rainfall, particularly in the coastal regions. And here I just took the one model results, so the IPSL. And this is showing on the left the amount of days with rain and positive Celsius. So with rain, positive Celsius temperature, we see a lot of, again, rainfall days along the coast. And on the right, we see an increase. So for the SSP 5 8.5 scenario, the end of the 21st century compared to the present time. So we see that there is increase in rainfall. So why this is all important is that because when we talk about the atmospheric rivers, we are talking about both impacts on the increased moisture and increased precipitation, and also increased rainfall. And then I will also talk about the melt. And here I'm showing I will show what are the atmospheric rivers in Antarctica. So overall, the definition of the atmospheric rivers is they are long corridors of anomalous moisture transport, and they're mostly associated with exotropical cyclones. And here we are talking about atmospheric rivers which have a strong meridional component, which are reaching the polar regions. And here I'm showing the two examples of atmospheric rivers reaching Antarctica. So, and these were the really important events which contributed a lot to the surface mass balance in East Antarctica. So it was in joining Maudland in 2009 and 2011. There were two anomalous years with anomalous precipitation in joining Maudland. And they were associated just with several atmospheric river events. So one of the examples, so for 2009 and 2011, I'm showing here. So that was the first time. So it was the publication I had in 2014 when we connected the atmospheric rivers to precipitation in Antarctica. So the impact on precipitation. So I will first talk about the extreme snowfall event. So if we just take this one event in 2011, affecting joining Maudland, and we know that it was extreme precipitation also from observations, because we had radar observations at Princess Elizabeth Station during that year. So on the atmospheric river shows really strong meridional components. So these colors here, it's the integrated water vapor in centimeters, and the arrows show the integrated vapor transport. And we see that there is a strong blocking of the rather deep cyclone, which is just in the near the joining Maudland, and it was associated with a really strong precipitation amount. So it was over the Southern Ocean, and the peak precipitation over land. And then when we look actually at the bulk of precipitation over different surfaces, so over the ocean, so this is in blue here, we see that it was starting and it was really the majority, if you talk about the aerial amount over the ocean precipitation. And then we had also the peak over the land, and also it's important that we had precipitation over the sea ice. So if you look into the well, more details of this event, so it's actually we had a lot of precipitation over the entire Jonian Mountain. So, excuse me, jumping. So we had the so here we show so this is the timeline. There were 2 peaks of precipitation, and it was really a large area of Jonian Mountain that was experiencing this precipitation, but the peak was really here in the escarpment and coastal area, and we were lucky with the location of the Princess Elizabeth Station to capture this precipitation. So we have really these two important peaks, and overall the accumulated precipitation was about 25% of the total annual precipitation at the Princess Elizabeth Station. So just one event. So it was really a lot of snowfall. And if you look at the just the structure of the atmospheric river event, so it's quite the complicated picture here, but the color, so it shows the integrated vapor transport and the with the mean sea level pressure, and we see the cyclone located associated with the cold front, and just in the warm sector of the cyclone. So we have the pre-cold frontal convergence and really strong moisture transport. And actually there was so the moisture was coming from subtropical latitudes. So here we know this because we are doing the back trajectory analysis. So here shown on the bottom. So these are the trajectories associated with the precipitation. So here in the box that was during the peak of precipitation event. So this 5-day trajectories show that they were extending all the way to the subtropical ocean and the Atlantic Ocean. And then we have the moisture uptake here in the contour lines. So they're showing the moisture uptake right in the subtropics, and there was the some local contribution of the moisture uptake as well, but the majority of the moisture was coming from the subtropics. So this event is so it's really linking the subtropical evaporation to the precipitation in Antarctica. And again, if we look deeper into the structure of the atmospheric river, so we see that there is a really strong low-level jet, like so it's near the surface. So we have greater than 30 meters per second wind speed, which is associated with the strong moisture flux. So this is in green, so shown the peak and the moisture flux, and we see that there is the more or less correspondence of the peak and the moisture amount. So these are the blue lines, and the yellow lines, this is the low-level jet. So this is the cross-section. So when we look along the atmospheric river, so we see that the strong low-level, the strong winds correspond to the strong moisture flux. However, if you look at the different locations, so over the ocean and near the Antarctica, so we see that over the ocean, so this cross-section here in the mid-latitudes, we see that this low-level jet really collocated with the maximum of the moisture transport, and it's really near the surface below 900 hectopascal. While when we look at the cross-section near Antarctica, so we have this decoupling. So we have the low-level jet near the surface, and the moisture transport is actually at the elevated heights. So that was an example just of a case of atmospheric river. And if you look at the impact of atmospheric rivers over Jonian Mountain here, so it's the composite over 10 years of the atmospheric rivers. So here in colors, compared to the median, so this all the gray lines is the median values for each of the parameters here. So the temperature, specific humidity, wind speed, wind direction, moisture transport with the zonal and meridional components. So the gray is the median, and we see that the composite for atmospheric rivers, they have really strong, showing the extreme state of the lower troposphere. So for which is important for the moisture transport that I have highlighted right now. So we see the excuse me, the strong increase in specific humidity associated with atmospheric rivers and increase in the moisture transport. And if you remember this, oh, I'm sorry, I don't know why it's jumping, maximum moisture transport that is decoupled. So it's really at the elevated moisture advection near Antarctica, so at the Antarctic coast. So we see here, this is the, it's really important to capture this moisture transport maximum. And we actually have really problems with the reanalysis and with the models, the large scale and regional climate models that are not capturing this maximum moisture transport. So not only the moisture transport, but also the temperature increase is important. And here we see that the compared to the median temperature, so this is the annual temperatures. So the composite for atmospheric rivers, they show the that the temperatures are close to zero. So which is important not only for precipitation, but also for melt and precipitation is rainfall. So if you look at the climatology of the events, so the here the reanalysis-based climatology for atmospheric rivers showing that they are really rare events. So we have maximum like 5 days or on the order of 2 or 3 days per year that we have the persistent atmospheric rivers over the Antarctic coast. And at the same time, we have important impact. So if you look at the snowfall impact of atmospheric rivers, so we have, so here on the top is the, so snowfall percentage on the left and the total snowfall impact of atmospheric rivers on the right. And we see that the like 10 to 20% of snowfall over the coast is explained by the atmospheric rivers. Which is an important in terms of the numbers. So up to like 100, 150 millimeter per water equivalent per year that is explained by atmospheric rivers. At the same time, they are causing not only snowfall, but also rainfall. So in here, the plots on the bottom show the contribution of ARs to rainfall. And we see that it's also about 10 to 20% of rainfall around the so Southern Ocean near the coastal Antarctica, and it's really important contribution to the rainfall over the Antarctic Peninsula. So this is the total snowfall and rainfall, and if you focus on the extreme snowfall events, which if you remember at the beginning of the slide, I showed that it's really important contribution to total annual precipitation. So here if we look at the most extreme events, so the 99th percentile, so here on the bottom right, so we see that it's the majority of these events are explained by the atmospheric rivers. So despite their rare occurrence, they have really important impacts on the extreme precipitation. So that was about precipitation, and then so I will quickly touch on about the melt impact. So they are, as I showed, they have important increase in temperature. So they have both moisture and temperature increase associated with atmospheric rivers here in Antarctica. So in here, the ARs that arrive to the West Antarctica, so they show actually the anomalous increase in the near surface air temperature. So here on the bottom, on the top plot, and in the bottom is actually showing the MAR regional climate model MAR simulated surface melt over the West Antarctic and Antarctic Peninsula in summer and in winter. So when we see this is the percentage of the AR contribution to the melt in the Weiss and Antarctic Peninsula, and we see that in summers they contribute to the important so up to like 80-100% even in the parts so the Mary Birdland and the parts of the Ross the ice shelf in summer, but not at the other areas where the melt is actually it's common in summer, but in winter we see that there is an important contribution to the melt. And we have actually several major melt events that are associated with atmospheric rivers. So we see that melt is infrequent in winter, but at the same time, the majority of this melt events are explained by the atmospheric rivers. And what is important here is that, so if you look at this specific, so a case study of a melt event in winter, so this is in May 2016 on 25th of May. So it was a really large melt in the Weiss and Antarctic Peninsula. So this is an atmospheric river that was causing this melt. So and we see again this typical structure with the blocking on the right, like in the low pressure system to the west. And what is important is that it's associated not only with a large integrated vapor transport, but with my time is over, but also with the increase in the cloud liquid water content and also cloud ice water content. And here, so we are showing the increase in the cloud net radiative forcing. So if you look at the specific points, so here as I'm showing, so here on the map, so that was the location in the on the Larsen ice shelf, so this point E. So here this showing the composites of the changes associated with atmospheric rivers. So we see that we have an increase in the integrated vapor transport during the atmospheric river events, but at the same time, we have also the downwell and long wave associated with the increase of the cloud water path during the same atmospheric river event. And here we also have an important Föhn impact, so the sensible heat flux. So we have a mixture of impacts that are actually causing the surface melt. And so as a conclusion, so when we talk about the atmospheric rivers influencing the polar latitude, so we have, so here it's a complicated slide showing actually the feedbacks that are associated with the increase in temperature, so the changes in the Arctic, both Arctic and Antarctic. So in here I highlighted in green, so the part of this complicated system is atmospheric heat transport, so which is the also big contribution from atmospheric rivers. And if you look at actually at the different components that of the system that atmospheric rivers are influencing, so we see that it's really a lot more than just the atmospheric heat and moisture transport, because we have an influence in this, the extreme state of the lower troposphere, so the changes in the lapse rates, the changes in the moisture advection, the increase in the water vapor, the cloud, liquid and ice content, the cloud radiative forcing, the melt and precipitation and so on. So we have really complicated impacts of the atmospheric rivers. And so I have two more slides just to highlight the work that is ongoing now regarding the observations. So we have the year of polar prediction, where we have been targeting also the atmospheric rivers to understand their complex nature and impacts. So and here is an example from the summer year of polar prediction measurement of an atmospheric river that we analyzed using different projects with measurements located in Punta Arenas and also at the King George Island, so at the King Sejong station, the Korean station and the Chilean Escudero station. So we put together these measurements to analyze an atmospheric river event. So it was really an interesting event that was stretching from Pacific Ocean via influencing the southern South America and then arriving to the Antarctic Peninsula. So this event, it was really an example of the complex phenomena and how to improve its understanding using measurements, and also looking at the inability of actually models, so radiosondes and the regional climate models to simulate, well, ability and problems to simulate this event. And this is an example showing the vertical profiles comparing the observations. So this is the solid line to the reanalysis. So we see that this important increase in the moisture, elevated moisture and also elevated temperature is not captured by reanalysis, which is that's really important to continue observations and its comparison. And also an important transition from the snowfall to rainfall. So this we show in the specific event. So we have the increase in the precipitation. So we have the peak. So here, so this is the WRF simulation. So the peak and the snowfall and also the rainfall. So in green, we have the rainfall. And we see, so this is the different phases shown by the symbols. So we see the snowfall in blue and then rainfall, again, snowfall, mixed precipitation in magenta. So this is rainfall, snowfall. So this is what's happening during the atmospheric river events. We have the snowfall, rainfall transition, and it's also an important question, what will happen in the future and how the models actually reproduce these events. So in the year of polar prediction that is happening now, so we have finished the summer stage, and actually now we are planning the winter measurements, which will happen in April, from April to July 2022. And this is now in the planning stage, and the atmospheric rivers will be part of this targeted observing periods that will be measured all around Antarctica at many stations, and we will be connecting with different projects and also with the modeling studies. So the goal is actually to improve models and improve the present day and the projection for the future. So thank you for your attention, and I will be happy to get questions.
Thank you very much. That's great. Okay. Does anyone have a question?
I have a question first.
Okay, John.
Thanks, Irina, for the very interesting talk. I'm an oceanographer. I'm interested in the salinity response. You know, the Antarctica River can transport a lot of more water towards the, you know, some ocean surface. Do we have some evidence, observed evidence for the salinity change?
Yeah, that's an excellent question. Because the impact over the Southern Ocean is intense precipitation and intense rainfall, and this should have an impact on the surface salinity. So we have not looked at the connection between the atmospheric rivers and the salinity yet. So the climatology of the atmospheric rivers has been still only connected with the precipitation over the ice sheet, but it will be really interesting, yes, to compare to the impacts on salinity. But I wonder what would be your advice to look at, so which measurements we could use this, or can we actually trust the models in this regard? Because as I understand that there is really, so it's not very, well, there is a link between the increase in precipitation and the salinity, so the intensified hydrological cycle, but also there is really strong impact of the melt, so the melt of the sea ice, right, and the melt from the ice shelves. So I wonder if we can actually, if it's easy to capture the signal and separate from the melt signal. So I'm not sure if it's really easy to do the separation of the signal separation.
Oh, yeah. So as we know, so Antarctica River can both transport moisture and heat. So particularly in winter time,
Right.
that can give a freshwater input at the ocean surface and also suppress the sea ice formation, freezing. So probably we can see a strong response to this for the salinity. So probably we can try to see some, seal data. I'm not sure, just I'm very curious about this. So I don't know where we can find the data at the surface to see the signal or the forcing. I'm sure, after we know where the river is, we can try to search for the data in the ocean. Yeah, maybe it is possible to look at this.
Because that's because that's one of the methodology, so the approaches that we are now developing for the winter year of polar prediction measurements. So when we have this, we will have this targeted observing measurements, And the goal is to connect the atmospheric and oceanic measurements. So it will be really, and that's an important question. So it's because when I'm talking about this, the difficulty of separating the signal, because we will have both impact on precipitation and impact on melt of the atmospheric river. So we can say, yeah, it's if it's salinity changes from the atmospheric river, but it's both from the sea ice melt maybe and from the precipitation, but we can at least see the signal maybe in the specific event. So that will be really interesting, yes, to measure it simultaneously.
Yeah,
because we tried it like during we had the ACE expedition. So when we were targeting the salinity, so we're doing salinity measurements along with atmospheric measurements, but we could not really capture the atmospheric river events because we're on a ship and the ship was avoiding the bad weather events. So we could not actually capture this, but
Good question, Jeremy. Thank you.
Okay. Yeah, thank you.
Thank you. Yes.
Anyone else have a question?
I have a question, or maybe a comment and then a question. So thanks for the talk. It was really interesting. I learned a lot. Is the net effect of atmospheric rivers one always of melt, or maybe on the coast, East Antarctic coast, it's more of a net effect over all the events of accumulation? And then I guess the second one is, can we separate out the effect of, if it is a melt event, from the heat flux versus like liquid precipitation leading to enhanced melt at the surface?
Yeah, another excellent question. Thanks. So your question points to the fact that atmospheric rivers impact both, and it's really regional and very season and event dependent. So that's what we're trying to separate right now. So I don't have an exact answer, but what I can say is that on the we see that in Greenland and Antarctic Peninsula, so Greenland coast and Antarctic Peninsula, so we have the mostly melt impact, while, for example, Johnny Mountain, so this is more precipitation, snowfall, increase impact. So again, it's really region dependent. So for the WISE, it's winter, summer, there is a more seasonality. So and again the regional dependency. So it's very it's not easy to separate. And again, but we see this so for the peninsula, like, and the like Johnny Mountain, the contrast is one has more snowfall, one has more the melt impact. So, and for the cloud, so that we have the increase in the liquid water content. So yes, this is what we see in both winter and summer events and the atmospheric rivers that we have. It's both increase in the ice, cloud ice content, and it's really significant in the ice content as well as the liquid content, and the strong downwell and long wave, so radiative forcing in winter. And in summer, it's a mixed, so because we have the increase in the short wave cooling as well, and so we have this really the daily cycle. So we have during the day, so it's more cooling, and during the night we have like more warming. So that's again the peninsula, which is more like mid latitude. So it's again it's a double. It's double, triple, yes. So it's both melt and precipitation, and the problem is that we don't yet. So I would not trust reanalysis that we are still using for the large scale. So impact on the precipitation. So they do not capture well, especially the snowfall rainfall transition. So because this is again it's big impact on melt from rainfall, and they're just not capturing the correctly. So
Great, thank you.
Yeah.
Thanks. Any other questions? I've one following on from that. So you mentioned that atmospheric rivers explain between 20 and 30% of the total precipitation. Do you have a sense of how uncertain that number is in terms of representation in reanalysis data sets?
Yeah, it's a good question. So this comparison was done using the algorithm by Jonathan Ville. So he used different reanalysis. So in the I had a no, I didn't put it in the presentation. So I had the time series because he compared different reanalysis and showing that there is the year-to-year differences between the reanalysis in the atmospheric river detection, and then it also influences the impact on the precipitation. So the comparison was done for the number of atmospheric rivers, and as reanalysis is different in resolution and in the physics, so we actually so identification of the ARs differs between the reanalysis. So while the impact was done using the ERA5 and MERA2, and I don't remember now off the top of my head the percentage, but there is so between these two reanalysis, there is a like maybe 5 to 10% the difference. But it's much larger compared to the other analysis, like GRA, for example, it's really coarser resolution. And so we compared, compared for the Arctic. So we have in the number of the atmospheric river detection, it's it's large differences. So that's part of the ARTMEP, so this atmospheric river tracking intercomparison method international initiative. So it's led by Christian Shields and others in the US, and it's really a large international initiative. So we are comparing different atmospheric river algorithms, and there are a lot of 30 of these algorithms. And different reanalysis and different models. And for now, the conclusion is that the uncertainty is huge, really huge. So, and for Antarctica, so we have two regional algorithms. So there is Jonathan's and mine for Antarctica. And for the Arctic, for Greenland, there is also another one by Kyle Mattenly. And so now we are in the process of comparing these algorithms. So yeah.
Interesting. Yeah,
so that's yeah.
You've actually answered a couple of the other questions I had.
Yeah.
That's really interesting to hear about that study. So actually, one of the things I was wondering about is just about the dynamics of how these things get set up. It looks like there's often a lower pressure system that doesn't move very much. It remains quite static, and I just thought that was interesting because in other aspects of meteorology that I've worked in terms of stable situations often have a high pressure that dominates, and but it looks to me like the dominant feature there is a lower pressure system. I mean, how much do these move during the events? Do they stay quite stationary, or do they move around a lot? Well, not much, obviously, but
so when we're talking about the ARs with the landfall in Antarctica, and also like poleward transport, so in the Arctic as well. So that's when the blocking is really important. So otherwise they do not have this meridional component. Unlike the ARs reaching Antarctic Peninsula, because there we can have also zonal ARs. But if you're talking about the ARs reaching Antarctica, so it's so the blocking is really important. Otherwise, we just don't have the meridional transport. So the stationary, it's again, they differ a lot. So we can have ARs lasting half a day and some up to 3 days. So that's really they can be of different nature and different persistence. So because this event, for example, I'm showing now, I don't know if my screen is still being shared. So we had the 3 days. So it was starting on 14th February and finishing on the 17th February. And there were actually the reinforcement of the precipitation by the mesoscale cyclone forming during the AR event. So it was a double system. So it was the atmospheric river maintained, so first by the large scale circulation. And it looks like the subtropical moisture export was actually feeding the formation of the mesoscale cyclone. But then there was this hiatus in precipitation, and then the AR was staying while the mesoscale cyclone was forming, and it was reinforcing the precipitation. So, and it was still the same quite stationary atmospheric river structure, but the dynamics was changing. So this is what's interesting, because we can have several extratropical cyclones and one AR, and then the cyclone can already lose its front, but the atmospheric river is still staying. So it's quite, so it's linked by the extratropical cyclones, but it's not that it's cyclone AR direct relationship. So it's
That's interesting. I hadn't appreciated that. Yeah, okay. So it's more about the sort of broader meteorological setup where you have a warm, just this link to the subtropics and warm, moist.
Yeah, you need extra moisture. So we have, I mean, the influence of cyclones like on Antarctica. So that's yeah, so that's what where we get precipitation. But it's the intense events and the AR events. It's really when we have anomalous moisture supply. And what we see also, so in this work, we found that there is not much, so this is really specific for Antarctica, because we have warm air over cold ocean, which is different from the mid-latitude ARs. So we have really suppression of the local evaporation. So we don't have much of the local convergence. We have really a long distance transport. So here it was really subtropical moisture, and there is a suppression of evaporation all along this AR. So I'm not showing this plot here, but you can find it in the paper. So there was no evaporation along the AR. So it was all coming from the subtropical. So, but it was maintain the upper level moisture transport. So it's quite, yeah, it's rare and quite intense.
That's great. We've been going for a while now, so we should probably end it there, but it's been really interesting to hear more about Antarctic atmospheric rivers, and we can continue discussions on Slack if you want to as well. And for everyone else watching this recording, you can ask questions on Slack as well.
Thank you.